Thanks everyone for coming. So we're happy to have Sami Davies here from UW. And she's going to tell us about trace reconstruction. So take it away.
Yeah, thanks very much for inviting me. Happy to be here today. So maybe a quick disclaimer. I know that this is a probability seminar. I'm not a probabilist. I am currently a math grad student, but I mainly do like theoretical computer science research. So yeah, I'm a grad student at the University of Washington. And this next year I'll be joining Northwestern as a postdoc in the computer science department. And so what I wanted to do today is I'm not really here to sell you on any work that I've done. Instead, I really want to sell you on a problem. There's a problem that I really like that I've been working on for a few years now that I am probably leaving behind. And a lot of the best work that's been done on it has been done by probabilists. And I would love for you all to think about it or share it with your students or colleagues or whatever. In particular, I think it's really taken off in the theoretical CS community, and I don't think it's taken off in the probability community as much from what I understand. But if people know this problem, you should correct me if you disagree. Okay, so what's the problem? Today we're going to talk about trace reconstruction. And so let me begin by just telling you a little bit about the problem. So what is the trace reconstruction problem? We have some unknown string X, a binary string, so its inputs are just on zeros and ones. So this unknown string X, and we're going to get to see some noisy samples from this string. And so the samples that we're going to see are going to be of the form that X goes through a channel, which we're going to call a deletion channel. And the deletion channel deletes each bit of the original string X independently with some probability Q, this deletion probability. So let's look at an example here. And I should say that we are going to call our set of noisy samples traces, hence the trace reconstruction problem. So given this input string X up top here, you might see these samples that I've listed down here if you have deletion probability of Q equal to 1/2. So what this means is, this string X goes through a channel, each bit is deleted with probability 1/2. So for instance, maybe we see at first these shaded bits here are the ones that are deleted. And so when they are deleted, we end up with this last trace down here. So it's not like you get a sample and then that same sample keeps going through a deletion channel and incurring more errors. It's each time you get out a fresh noisy sample. Okay, so the parameters to keep in mind about this problem are about deletion probability Q, which is the probability that you delete each bit. You can think of Q as being 1/2. Most of the things we're going to talk about today are for constant deletion probability. If I'm ever not dealing with constant deletion probability, and by that I mean maybe I'm dealing with deletion probability 1 over root n, something very, very small like that, I will say so beforehand. So I've told you our setting. I haven't told you what we're trying to do yet. So our goal for this problem is to recover the unknown string X with probability at least 1 minus 1 over n, or I will continually use the phrase with high probability, using as few traces as possible. Okay. So this is my goal for trace reconstruction. I want to take as few of these noisy samples as I can and reconstruct the original string exactly with high probability. But there's another way that you could really view this problem when you're viewing it as an exact reconstruction problem. So maybe, instead of writing down this goal, especially because you all are probabilists, maybe something that might be a little bit more clear to say is that kind of the goal is to distinguish between the distributions of traces produced by any two strings. Okay, so what I mean by that is that if I give you like two strings on n bits, maybe they only differ in like 1 bit, so they look exactly the same, except like, you know, at one spot there's a 0 and one spot there's a 1. Kind of the question is like, how many traces do you need in order to observe that difference? So the example that I gave you actually happens to be very easy if you know, or like if the strings actually only differ in 1 bit, it's easy to distinguish. Or by easy, I mean it's like we know how to distinguish in this case, but generally speaking, we don't know how to do this with as few traces as possible. So I'm going to tell you a little bit about motivation and a little bit about what we know about this problem already in terms of this sample complexity. Are there any questions on the problem setup? Okay, then we will move on. Something kind of cool about this problem is it relates to this topic of information theory and coding theory and computer science, which you know, have been around for a long time. But more recently, this trace reconstruction problem actually arises in this computational biology setting of DNA data storage. So there are these like big industry labs that have been doing these like have been experimenting with storing data as DNA. With the reason being that DNA is like extremely long lasting. So this is a way to store your data in a way that like isn't going to change as technology changes, or is not going to be what's the word I'm looking for? Like is like obsolete as other ways that we have to store data. So this is very cool, but in like the way that we store data in DNA and the way that we retrieve it, there's errors incurred. And so this trace reconstruction problem is one way of representing how some of the error is incurred when you're trying to get back the data, basically. So that's all I'll say about that. For motivation, it kind of fits in with like a framework in like statistical reconstruction, information theory, all these other fields as well, though. All right. So what do we know about this problem so far? There's been a bunch of work. I, you know, have down some names here. You're, you know, probably familiar with, you know, some of these people. But really the main things that I want to say about what's been done before is that we know that the minimum number of traces needed for trace reconstruction is at most exponential in some large constant times n to the 1/5, where remember that n is the length of the string. And the number of traces needed is at least some other large constant times n to the 3/2. So, you know, you see these things, and the point that you should really be getting out of this is that there's an exponential gap between these upper and lower bounds. Okay, so this is very bad. And it's not like that, you know, these this upper bound is from 2017. And people have been thinking for, oh, sorry, this upper bound is not actually from 2017. Kind of like the main technique from this upper bound is all the way from 2017. And I say all the way, you know, like we've been thinking a lot about this problem. We would generally expect results in this field to be moving like a little bit more quickly. And the point is that, you know, a lot of people have thought about this, and overall people are pretty stuck. So we're pretty stuck, and instead people have turned to variants of the trace reconstruction problem. All right, so I explained that there's this upper and lower bound, and then I kind of glossed over some of this other text that I had up here. So let me zoom in on it for just a second. So what do we want to say here? Let me focus on this section right here for a moment. So first off, this result that exponential in n to the 1/3 traces suffice. So up here, when I write this big O notation, first off, I'm hiding a constant here. So this big O is meant to hide that, it's really like some constant C times n to the 1/3, like, how I wrote down here for that n to the 1/5. And similarly, if I write this like capital omega of n or capital omega of something, that means that it's at least some large constant times n, or at least some large constant times something, similar to how I wrote down here. And to kind of motivate some of the techniques that we see on the trace reconstruction problem, what I actually am going to start with today is I'm going to show you a rough outline of what is called a mean-based algorithm. So this is a result that's due simultaneously to Day, O'Donnell, and Servideo, as well as Nazaroff and Perez. And it's like mathematically very, very beautiful and leads to a very clean result, and has a lot of cool math behind it. And in particular, this n to the 1/3 result is, not that far off from this like n to the 1/5 being the best that we have so far. So with that kind of motivation in mind of what we know so far and what the state of the art is, the state of the art being that there's this exponential gap between upper and lower bound. So instead we've turned to variance. What I'm going to do today, so far I've already given you a bit of background on the trace reconstruction problem, so we're already done with that. I want to give you a rough sketch of this exponential in C times n to the 1/3, that upper bound. So I'm going to give you an insight into this, like what a mean-based algorithm is. And then after that, I want to give just some examples of the variants of trace reconstruction that have been studied so far. So this is where my work has been in like variants of the trace reconstruction problem. And in particular, I'm going to explain this specific problem of approximate trace reconstruction, which I will formally define in like whatever, a half hour or so. But let me say for now that, the problem that we set up so far is you have to reconstruct this original string X exactly. So maybe you say, why do I have to reconstruct exactly? Let me relax this and instead just do this like with high probability or something like that. Or sorry, just do it like approximately. So I'm going to then present our result as a lower bound on approximate reconstruction as well. Also, I didn't see Yuval was there until now. Hi, Yuval. So yeah, obviously we know Yuval. Very funny. So I'm just curious then, if people don't mind giving me like a show of hands because you have reactions. How many people are familiar with this result then? Okay, I saw like 2 hands, 3. Okay, so not enough there's not enough hands or thumbs up. Okay, I see 4. So if there's not enough hands or thumbs up, then I'm gonna feel bad talking about it then. If you know about it already, you don't have to listen. You can check your email for 15 minutes or something like that. That's fine. Great. So, whoops. So before we get started on that, let me pause here and ask if there are any questions on the past work or anything like that. And obviously, Yuval, if you have anything you'd like to add in at any point, I would be happy for you to do so. So please feel free.
Thanks.
Okay, otherwise we seem to be good to go. Also, at any point, I kind of have like multiple screens up. So if you'd like to say something in the chat instead, I'll be able to respond to that. So please feel free to do that instead. Okay. Great. Then let's move into our sketch of this exponential in n to the 1/3 upper bound. All right. So what I'm going to begin with doing is I'm going to like very quickly derive for you like a generating function for this problem. And this notation is due to the Nazaroff-Perez paper. So if you'd like to kind of check anything in there more thoroughly, that's the paper that would most line up with the presentation that I'm going to give. So let's go ahead and lay out some notation. So I'm going to assume that we have a string on n bits, where the bits are labeled A0, A1, all the way up to A sub n minus 1.
A question, what is delta in the theorem? So there's a delta in the hypothesis, but how does it enter?
Oh yeah, thanks. Delta is related to it's related to the failure probability here. So you're gonna like succeed with probability like 1 minus delta here. So that delta is, yeah, maybe I missed it in the theorem statement exactly how I wanted to say it. Yeah. I should have said reconstructed with probability like 1 minus delta or something. Thanks for that. Okay. All right. So we're going to begin with this string of n bits, A0 to A sub n minus 1. And we're going to consider the trace of A by this A tilde, where bitwise, we're going to say that A tilde is equal to like A0 tilde up to, it has some length, maybe A sub m tilde. And then we're going to append zeros at the end of it so that it is of length n. All right. So with this notation, I can study the expectation of this polynomial here, where I'm going to think of w for now as being like our variable here. In particular, w is going to be this this complex variable. And so looking at this expectation, we can begin just by moving the expectation inside of the sum. Nothing too crazy going on in any of this calculation, so I'm just going to run through it rather quickly here. And then when we're looking at the expectation of like what's going to be the bit that ends up in position j in the trace, one way that we really want to do that is you can think about, well, I need some bit to be kept, so I need to not delete something, and then for every bit k which is at least, or every position k which is least as large as j, I want to look at the probability that the bit at position k in the original string shifted to the bit in position j in the trace. So that's going to be the quantity that we unpack a little bit here. And then unpacking that, we'll just end up with that label AK. And then we'll choose the positions that we delete, and then we'll keep the right amount so that indeed the bit at position K is shifted to the bit at position J. Okay. So then with that, we can just rearrange the order of the sum. And then doing that was going to give us this nice expression here. In particular, we can see that this term in the sum is going to be just 1 minus q times w plus q to the k. And so then folding everything together, we end up with this like nice closed form for our generating function. And if you want to consider a change of variable on that complex variable w, you can end up just with this new complex variable z instead. So overall, let me just zoom out for a sec. So overall, the point is we can study these like these complex polynomials of the form the sum over k from 0 to n minus 1 of 1 minus q times ak to the zk for z, some complex analytic variable. Okay. And so now that we were able to construct a generating function here, this is the main technical part that I'm going to skip over, although I can say a few words about the proof. The main technical part here that's like going to be using the structure of these generating functions is I'm going to say that for all distinct pairs of strings I could take on n bits, then there's going to exist some bit j where basically in expectation the strings are going to look different. So I can say that formally, and then we'll say it informally. So in the expectation over the traces, the bit that we see in position j is going to be substantially different than the bit that we see from B. Okay. So let me just say that again. There's some bit j, where in particular j is going to depend on those two strings, A and B, where in expectation, A and B look substantially different. All right. And I jotted down just a few quick notes about the proof of this. Basically, once you have the form of the generating function, the proof is not too bad once you're able to use this result of Borwein and Erdely, which is about the modulus of a complex analytic function on like some arc of the unit disk. So given that you know that like every complex, so in particular complex analytic functions whose coefficients are either like 1, -1, or 0 are going to have pretty large modulus on an arc of the unit disk at some point there. So let me there's no questions on that. I'll continue through this proof sketch so far. So again, all we've done so far is we've shown you can drive this generating function. And then I said that through doing some analysis on the generating function, you can show that for every pair of different binary strings on n bits, there's some position where in expectation, the traces are going to look rather different at that bit. And so now I'll write out our algorithm for our algorithm that we can actually have for this reconstruction now. So we're going to say that a string A beats a string B, which really means like A is a better match than B for the traces. If given these t traces, x1 tilde to xt tilde, at the position where we know that A and B should look different, we have that this difference on the left is less than this difference on the right, which is really here just going to mean that the string A looks closer to the traces at bit j than the string B. Okay, so looking at this thing here, it's like saying, well, on average, how do I expect the traces to look at that position j? Yeah, so we're just saying who looks closer to the traces at that special bit j. So if A looks closer than B at that bit, then we say that A beats B. And now we can write our algorithm down, which is really very simple. We're going to output the string x hat in 0, 1 to Vn that beats every other string. And if no such string exists, so maybe you have like no string that beats every other string, then you can just whatever, output anything. You can output a random string. Okay. This algorithm is really very simple here, and this is kind of it. Like the point is that this algorithm works, and the analysis that this algorithm works is basically just it's just a Chernoff bound plus this main technical lemma, which we saw up here. So with high probability, the string that beats every other string is in fact the right string. So I know this is the part that some people were familiar with. Let me just take 1 minute to recap, and then we can take some questions. So we are sketching out this exponential in c times n to the 1/3 upper bound. And the proof is really very, very nice and very clean. We're able to drive this generating function. Once we have the generating function, we can use this result about complex analytic, or I should just say complex polynomials that have coefficients of 1, -1, or 0 in order to derive this result about this like special bit j for every pair of strings. So that was our main technical lemma. And then using our main technical lemma, you can prove that just outputting the string which beats every other string, meaning which looks closer to the traces at that special bit compared to the string that you're comparing it against. So I'll pause here for a moment. If anyone has any questions on this, otherwise I'll just say like a few words to wrap up this section, and then we'll move on to trace reconstruction variants.
Are you going to say a bit about the n to the 1/5 improvement?
Yeah, that's exactly what I'm going to do next.
Okay.
And by I'm going to say a bit about it, I'm going to say like a couple sentences about it. I've unfortunately not even like had the chance to read the full paper yet. I've just gone through the abstract and intro, so I know the techniques. If you or anyone else has had the time to read it and wants to say a bit more words, that would be totally fine as well. But let me say the few words that I can say on it for now. Oh, okay. Well, maybe the first thing for those who don't know is that you can't do better than this exponential in n to the 1/3 traces, while the only information that you're using from the traces is like the mean position at bits. Let me write that different. So what I mean is that if we go back up to our algorithm, the only information that we use from the traces is exactly this, is exactly like for each bit, what's the mean of the traces there, and like what is shown in both these papers, which provide this exponential n to the 1/3 upper bound, is that if you're only using this this information, then you can't hope for any better upper bound. And so for a while, up until, I mean, I think Zachary's paper just came out, I don't know, like not that long ago, like a couple months ago. So for a while, people were very stuck with this. And in fact, there was even there was a rumor floating around that I was always under the impression that you couldn't do much better by taking substrings. But Zachary proved that you in fact can do better here. So Zachary Chase just very recently showed that you could get the upper bound of exponential in like n to the 1/5 by instead, and I'll zoom in a little bit because I know that my handwriting got a little small here. By like basically instead of only looking at instead of like looking at a polynomial where you're only looking at like the differences in single bits, instead you're going to generalize this to basically look over substrings, which is basically like what this more complicated looking term is doing here. So you could think of, you know, the mean based algorithm is like looking over substrings of length 1, And then this new result is looking over like longer length substrings. So if you're able to do that, then we can do a bit better and extend it to like n to the 1/5. That's all I'm able to say about that for now. I'm excited about the result, but I just haven't had time to read it yet. Since there's a few people who know about this problem, if they have anything extra they would like to add about that result, please feel free to. But otherwise, I'll pause there, and then we'll move on to some trace reconstruction variance work.
I sort of have a question. I'm not sure I understand where these exponents are coming from. So is
Yeah.
everything happening in the on the complex polynomial side? So
Indeed,
there's some
yeah.
magic happening there, and in practice, it doesn't seem to me that this is such an easy algorithm to implement, because you do have to compute which bit j is the magic one, right? And is that an easy thing to figure out or not?
No, you're right. So like as I've stated this algorithm, it is not efficient.
Okay.
There is like so if I'm remembering like the differences between these two presentations correctly, there's a presentation, the presentation given by like Dacevideo and O'Donnell. There's like a linear programming way that you can write this down and then solve it, and that can be like an efficient way to do this. But I'm not even 1,000,000% sure it extends all the way through. Yuval, do you know? Like,
yes. So by changing the algorithm using linear programming, you can reduce it. So the complexity is basically the complexity of looking at all the traces. That's the expensive part. And then the actual processing is faster. So you still have complexity of e to the cube root of n for that algorithm that Sami described. Just you need to look at all those traces.
Yeah, but you're not given at least that additional exponential piece, I guess, as Jacob was pointing out of, like checking for that like special bit. Yeah, it's a good point. And in practice, if you're interested, Jacob, from what I understand about, how this actually works in practice is that people use like different types of variants of this like bitwise majority alignment algorithm, which is really like a very simple algorithm where you take all your traces and then you like look at the position of well, it's mainly simple. You'll look at the first bit and all the traces, and you'll see like are more than 1 or 0. If the answer is 1, then all of the traces that were at 1, you like update their pointer to be 1 further, and then all the ones at 0, you like keep the same, basically. So it's kind of like you were assuming that maybe there was a 1 there and it was deleted, and you're trying to like account for that by like keeping the pointers back still. And there's a more complicated variant on this like bitwise majority alignment algorithm that you can look at, and I believe that these are actually like still what they use in practice. At least a few years ago, this was the case.
Thanks.
Yeah, sure thing. It's kind of a classic thing to like, motivate a problem with like, some practical example, and then like give you an algorithm that's like completely like not practical. And you're like, well, how did you help here? But yeah, good question. Okay, thanks. So, wait, did I miss something? Oh, whoops. All right. Great. So that's all I want to say on that. And that's kind of old hat in that, it's like 3-4 years old at this point. But I don't know, that's the piece of math that I wanted to write down that I thought might interest some probabilists. You should definitely check out like Yuval's exponential and n to the 1/3 paper if you have not seen that result and are interested in the techniques there. There's also, as I will describe soon, some other work here that might be of interest to probabilists. So some variants on trace reconstruction. I kind of said at the beginning that, a lot of people were pretty stuck in thinking about this like exact trace reconstruction problem exactly the way that I had formulated it to you before. And I think I'm first off just kind of showing you this big list because I want you to see that like there's a lot of work that's been done. And this is not exhaustive at all. There's like a lot of work on these different variants that have been done. But in particular, I'll point you to like maybe the most well-studied ones, or in my mind, the most well-studied ones. So this average case reconstruction problem, you're assuming that the input string X you have is like sampled uniformly at random. So in particular, that like with high probability omits certain bad behaviors that might make it like bad to reconstruct or harder for your reconstruction algorithm to deal with. For example, if you sample X randomly, it's not going to have runs longer than like 2 times log n or something like that. A run being like, you know, a bunch of ones in a row, a bunch of zeros in a row. So for some reconstruction algorithms, those long runs were causing problems. And and as you see here, as soon as you are assuming that you're, you know, pulling X uniformly at random, then the sample complexity is much better here. So we've gone from like exponential in n to the 1/5, all the way down to exponential in log n to the 1/3. So much better here.
Maybe one comment. I think what causes most problems are not long runs, but rather like similar pieces. If the string looks the same in different areas, that's the hard thing, you know. And in a random string, you know, every sub block of length log n is different, and that's
that's, I guess, like a more general, more correct way to view my statement on runs. So in particular, we'll look at strings that have like a long pattern of like long alternating like ones and zeros when we talk about like the lower bounds for approximate reconstruction, which is using some of what we know about what strings are hard to differentiate between the distributions of the traces exactly. Okay, so average case, I wanted to point out this coded problem has also received a good amount of attention. Kind of similarly, you're assuming that the original string X is encoded, so it has like some underlying structure, and there's a few different ways to formulate that, but this has also been studied. I like this problem a lot, population recovery, where maybe instead of having just one unknown string, you have like k unknown strings. And so when you're given, and you know, they maybe they look, well, okay, let's say you're given k unknown strings, and then when you get traces, you don't know where the traces came from. You don't know if they came from like that first unknown string x1 or like your last unknown string xk. So there are some results on like how you can hope to recover, like a population of unknown x's. In joint work with myself and then Mickey Rocks and Cyrus Rashtian, we looked at if you have labeled trees. So I told you, you know, trace reconstruction is you have a string labeled with zeros and ones at each bit. What if instead you consider a tree? So like think of like a binary tree or something that has 0 or 1s at each bit. We have some work on that, and there's been some nice follow-up work. My personal favorite recently, if you're looking for something recent to read on this, is this smoothed analysis framework, which was in SOTA of this past year. So in this smoothed analysis framework, what we really mean by that is you can take any string x prime, and this x prime might be like a worst case string. It might look very bad, as you've all said. It might have this like bad behavior of having like some substrings that look like some other substrings, which make it hard to reconstruct. But instead of trying to reconstruct x prime, we're going to perturb x prime, and we're going to form some string x. So we're going to form that string by flipping each bit independently with some like fixed probability sigma. Okay, so as you can imagine, as you like clearly as you make sigma larger and larger, this just approaches a random string. So this is like a nice way to interpolate, or at least I think of it as like interpolating between like worst case results versus average case results. And in particular, they show if this sigma probability is constant, then poly-n samples suffice. So if you have a constant probability of flipping each bit, then poly-n samples suffice to reconstruct that string exactly. Okay. So told you a lot about stuff that's been done before. And now for the rest of the talk, I'm going to focus in on a problem that we studied for the past while. And honestly, this problem turned out to be quite a lot harder to study than we'd originally hoped for. So I'm going to present a lower bound result today. So we were interested in this problem of approximate trace reconstruction, which I'm actually just going to define a little bit more below. So don't worry yet, I haven't told you what it is, but I want to tell you formally. So in order to tell you what it is, just to make sure everyone knows a little bit about distance metrics between strings. So we can measure the distance between two strings with a metric called edit distance. And I'm also going to mention another distance called Hamming distance. And let me explain what both of these are with this example I have over here. So for my edit distance, if I have these two strings x1 and x2, I say that the edit distance between strings x1 and x2 is equal to the minimum number of substitutions, deletions, and insertions to turn x1 into x2. And I'm defining this in the way that I want it, just like the minimum number of substitutions, deletions, insertions. You could consider a model, and often you do consider a model where maybe substitutions are cheaper than deletions or insertions. So like maybe each operation has some cost associated with it, and instead you want to know what's like the minimum cost of turning x1 into x2. Okay, so this would be my edit distance definition, and instead for my Hamming distance, the Hamming distance between two strings x1 and x2 is just the number of different bits between the two strings. So let me look at these two strings up here as an example. The Hamming distance between strings x1 and x2 are the number of different bits between them. So for instance, we see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we see that these two strings are different everywhere. So that their Hamming distance is going to be very large. It's going to be 14. And then I've set you up with a particular example where the edit distance, or sorry, the Hamming distance is really large, but our edit distance is actually going to be really short. In fact, if you would think about like shifting x2 to the right by inserting a 1 and then by deleting this extra 1 at the end. So that would be wait, that's just an insertion and a substitution. So that would be like an insertion and a substitution. Then the edit distance here is just going to be 2. Oh, I said substitution, sorry. If I just considered like a insertion of a 1 out in front, so let me write it like this. I put a 1 out in front, and then I delete this 1 at the end. Now these strings are the same. So that was my edit distance of 2. Okay, and so generally, because when we say that the Hamming distance is the number of different bits, this is really equivalent to the number of substitutions just to turn. Let me just say that actually. The number of substitutions to turn x1 to x2. So in particular, you can always think of the Hamming distance is always going to upper bound the edit distance between two strings. All right. So we're mainly going to talk about edit distance. That's the one to keep in mind here. But I will say like a sentence or two about Hamming distance then later. And now we can formally give our problem that I want to talk about today, which is approximate trace reconstruction. So our goal here is going to be to obtain epsilon n approximations for a given string x. So if we are given traces from an unknown string x and some like learning parameter epsilon, then our goal is to output this this guess x hat so that the edit distance between x and x hat is less than or equal to epsilon n with high probability. Move this up a bit. So let me pause there just to make sure the problem statement is clear. Let me just say specifically that our goal is still to minimize the number of traces needed. So we're minimizing the number of traces needed, but the objective is kind of different in that we only want to output something which is close in edit distance. We don't need to output something which is exactly right.
So is epsilon n clearly the right threshold? You could ask for it to be even closer than that.
I mean, yeah, you could ask for, I mean, I can let epsilon be 1 over n. I can let epsilon be,
Okay.
yeah, as
Epsilon
small
is
as I
not
want.
fixed.
Yeah.
Okay.
Yes, yeah, good point. Yeah, you can take epsilon to be a function of n. Yeah, I guess if you were thinking of epsilon as a constant, then it's a good question of like, yeah, is epsilon constant the right thing to study here? Yeah.
So for epsilon equals q, you could just take the first trace.
Yeah, in expectation, you just take one trace. Yeah. Yeah. Right. So you want to be able to do substantially better than that given more traces. Oh, and you know, because you bring that up, I'll also mention that there's a whole line of work. It's more in like the electrical engineering community that studies this problem from like a slightly different angle. They've been studying this problem for years. They would just kind of call it something different. Basically, instead of having access to a lot of traces and wanting to minimize the sample complexity, like to get the right edit distance, or like to get something within edit distance of the correct string with good probability, they would ask, if you give me 2 traces, can I do anything with that? So like if you're given a very small number of traces, even like heuristically, what can you do? So there's been a lot of like experimental work on this as well. All right, good. So now we'll move on to some motivation. And you know, I'm not a practitioner, but from the people who I work with who've like, you know, worked more on this like DNA data storage side of things, apparently like all you really need is like an approximate trace reconstruction for like that practical motivation that I mentioned in the beginning for the exact reconstruction problem. And this is more of an observation even, but let me state it anyway. Basically, exact reconstruction is going to be more expensive for some strings than approximate reconstruction is, and you can see that very easily just with some simple examples. So if I'm looking at the exact reconstruction of like the string, which is like a long run of ones with like some 0 hidden in the middle, plus another long run of ones, then we know that just to learn where the position of the 0 is going to take like at least order n traces. But approximately, this is going to be a lot easier. Approximately, you could learn Yeah, you can learn this with much fewer traces.
You can learn it
So
with-
like,
You don't need any traces, right? You just guess that it's.
yeah, yeah. Like I mean, that's why I paused, because I was like gonna write down a number, then I was like, no, like you could just do it. So yeah, right. I mean, like with epsilon, if you're taking like epsilon, I don't know, like a half, then obviously like this is, yeah, you don't even need a trace, just like output a random string. But you know, like more interestingly, you could take epsilon to be like really, really small, and you could learn it approximately like still with like very few traces. Like with like polylog n traces, you can learn this like, right, like very for very small epsilon.
Sorry, I guess I don't understand. When you say exact reconstruction of one string, it's not clear what are the alternatives. What is, so if that's the original string, if I know that's the original string, I don't have anything to learn. So I guess what I want to understand.
Oh, okay. So maybe here's what I mean. If I have an exact reconstruction algorithm, and this is my x that I input, I don't know if that's my x. I'm just inputting some x. An exact reconstruction algorithm will need at least order n traces to learn it exactly. Yeah, okay. So I guess in an approximate algorithm, then it's a good question. Yeah.
But I guess one formulation say, you know, the string has this feature. It's one of those n strings where the 0 is somewhere inside, and you don't know.
Yeah.
Right?
Yeah.
So maybe that's.
Yeah. Yeah, I think that's like the only way it really makes sense here. Like if I know about this, because otherwise approximate, like it's like, how are you going to know that you're right, I guess.
And I guess if you know that it's one of those, then an approximate, you just say, well, all ones is very good.
Yeah, yeah, right. Yeah. So yeah, maybe nothing hugely deep going on for this example, just meant to show that like these two problems are in fact very different. Yeah, maybe because of these kind of, you know, like silly edge cases that we don't, you know, it's not like we're maybe gaining a lot of intuition here, but still, these things are very different. Oh, okay. And here's, I know this is a little bit of a long sentence. Let me zoom in and we pause here for a moment. This is like an observation from some results on the K deck of a string that I really like. So let me explain what I mean here. So basically, if you want to be able to differentiate between two strings, x and x prime, and if they're close in Hamming distance, so remember that's just the number of substitutions between the two strings. If you want to differentiate between these two strings, then this is possible with like n to order k traces. So if they're close in Hamming distance, you can differentiate them. And we don't know that a similar statement holds for edit distance. So we don't know if two strings are close in edit distance. Is it possible to differentiate them with, you know, n to the order k traces for k the edit distance?
I mean, there is a recent paper that does prove exactly that. So we do know.
Who's it by?
I will reconstruct the author. I forget, but there is it just, you know, in the last couple of weeks. But still, that requires k to be, you know, k to be very, very small for it to be.
Oh, okay.
Right. So
all right. Yeah. So this is only interesting.
Right. So n to the k will blow up if k is epsilon n. This doesn't, and epsilon is.
I mean, we can take epsilon to be, yeah, something, whatever, log n over n or something like that. Like you could take it to be very small, and then maybe end of a log n is, you know, maybe you're happy with that.
Right. If you have a good approximate algorithm for epsilon, which is log n over n, that's.
Right. Yeah.
Do you mean here that k is a lower bound on the Hamming distance?
No, I mean upper bound. So this might be surprising.
Okay.
Yeah. Yeah, and again, this is let me just state, this follows from results on on the KDEC. So that would be the place to look for more on this. Okay. All right. So I've said what I want to say about the variance of trace reconstruction. I've explained to you the problem statement of approximate trace reconstruction. Today I'm going to prove a lower bound. And yeah, I'm going to prove a lower bound, and it's kind of going to use as a black box, like some of the results that we know from lower bound for exact trace reconstruction. I'll also say, I didn't realize this was an 1.5 hour long talk. I thought right? This is an 1.5 hour long talk.
Well, that's optional. So.
Oh, okay.
Some speakers prefer the longer format where you can go more into details. Some prefer standard, so it's up to you.
I planned for an hour-long talk.
Okay.
Yeah, I planned for an hour-long talk, but I'm definitely running a bit over. So what I mean to say is I'm running a bit over of my hour-long talk, but we have more time. But also I omitted a lot of details because I thought I only had an hour. So I'm giving myself a slight cop out here, but that's okay. So let me state our the theorem that I'm going to outline a proof for you for today. So suppose that there is some function f, where f of n traces are required to distinguish between two length n strings, x prime and y prime, with probability. I say 1/2 plus an eighth here. I say that because 1/2 and an eighth are going to come up in the proof later. Okay. And I mean distinguish between these like exactly in the sense we meant before. Okay, then our result says that there's some constant c star and epsilon star, so that if epsilon star is big enough and and c star is small enough, then any algorithm that epsilon n approximately reconstructs an n-bit string with high probability has to use at least f of c star over epsilon traces. So I'll let you digest this, but let me kind of say like I'll leave this here so you can still see it, but let me say like the overall message of what this means. So currently, f of n is at least some constant times n to the 3/2. I've kind of been dismissing log factors this whole time, so allow me to continue to do that. For instance, like what our result here would say is like n to the 5/4 traces are needed for epsilon n reconstruction. Let me say epsilon n approximate reconstruction with epsilon equal to, and like I said, we consider like epsilon to be of a function of n sometimes, so like n to the -5/6. So epsilon is rather small here. So overall, this means if my edit distance is allowed to differ by like n to the 1/6, if my edit distance can differ by like n to the 1/6 bits, then I'm going to still need like a superlinear number of traces here. Okay. I'll pause on the statement just for a sec if there are any questions. Otherwise, we're going to move into a proof outline. And I think I should mention the proof outline might be kind of similar to, something that you've seen for like the lower bounds on like the coded trace reconstruction work, if you're familiar with those. Okay. So let's begin with our proof sketch. Okay. So you can think of this function f as being, like the same thing that we had up here. we're gonna take two strings, x prime and y prime, which are strings on n prime bits. So notice our parameters are a little bit different to start with. And suppose that f of n prime is the lower bound on the number of traces to distinguish between these two strings, with probability a little over a half. Okay, so we can set some parameters. And the following work showed that you could consider taking these strings in order to achieve this. And I'm just writing these strings down so that you can kind of see what these strings look like and understand like what the hard, what we think the hard cases are so far in terms of lower bounding, or I should say what strings have proven good for lower bounds on exact reconstruction so far. Because we don't know, but these are actually the, the hardest kinds of strings. Okay, so what it looks like is we have some 0, 1 chunks, which we concatenate together, and then we have slightly different amounts of them being in like the front or back of a string. So like, for example, we could take x prime equal to like 0, 1, 0, 1, 0, 1. So like k equal to 3, and then insert a 1, and then we have 4 0 1s at the end. Whereas for y prime, we're going to have 4 of these 0, 1 pairs at the beginning, and then R1, and then 3 0 1 pairs at the end. All right. So we see that these strings are relatively close in Hamming distance. But as I said, we know that you need at least end of a 3/2 traces in order to distinguish between these two strings. And so what we're going to do is, given that we know like these hard strings to distinguish exist in the exact regime, we're going to construct two strings which are, or a string which is hard to learn in the approximate regime. So what we'll do is we're going to construct this string v by concatenating these blocks together. So these blocks are going to be v1 to vb. So I'm constructing my string like v1, v2, all the way up to vb, where b is going to be set depending on epsilon and n. And each of these blocks, each of the v blocks is going to be set to either be x prime or y prime uniformly and independently. So for instance, maybe you end up with like x prime, y prime, x prime, y prime, or something like that. And so what does this look like all together? You've just like concatenated like the hard versions of the string that we saw before. All right, so keeping in mind this string and knowing that it's like made up of blocks that are hard to distinguish, we're going to show that this string v is requires some number of traces to learn approximately. So let's assume that our reconstruction algorithm receives t traces where t is less than f of some constant over epsilon. So it receives like rather few traces, and we're going to show that it can't learn v approximately up to order like epsilon n without breaking the results that we know for the exact reconstruction problem. So in particular, I think I just wanted to walk a little bit about, So I want to show you just like our main lemmas here, but I need some notation to show you our main lemmas. So we're going to consider the distribution over the sets of t traces to be this distribution d sub I. And it's d sub I because I'm going to end up taking like considering b of these for b the number of blocks. Where, so for vi generating the traces for this distribution d sub I. And so then in particular, we can write down this distribution d sub I as being like a convex combination of the distributions f and g sub v sub I, where g sub vi is like basically the piece that you're like you're unsure of. Oh no, sorry. So G sub vi is like the piece of the distribution where you're given like some advantage on whether or not the trace is coming from the string x prime or y prime, and the distribution f is like you're not really sure which it's coming from. So let me just say like intuitively here. F corresponds to being unable to determine like whether vi is x prime or y prime with any advantage. And all I'll say about this this distribution of G sub vi is that you can make it basically by looking at all the t sets of traces, and you can look at whether or not they're more likely to come from like x prime or y prime. And so if a set of traces is more likely to come from x prime, then you can assign that like extra probability mass to x prime. And if it's more likely to come from y prime, then you can assign like the extra probability mass to y prime. So in total, then this gives you a way to like decompose this distribution into this like unknown factor where you get no advantage, plus this like factor of the distribution where you gain some advantage based on like the traces that you saw. Okay. And I won't go over this, but it's not too hard to show, but you can show that this gamma parameter is going to be upper bounded by a fourth. So what that means is that when you're sampling from this distribution di, it's like more likely that you're seeing like you're not able to get any advantage over guessing if vi is from x prime or y prime. And that's kind of like the main intuition here for why everything else is going to work. So in particular, now I'm able to define some definitions that I'm going to need. So for that string v, I have those b blocks. I'll say that the ith block is indistinguishable given the t traces that I have. If you can think of di as sampling the traces of the ith block from f. So that's a way to formalize that. And then our lemma here on the number of blocks which we're unable to distinguish is the following. So that we have for b at least like some large constant times log n, at least b over 2 blocks are indistinguishable with probability at least 1 minus 2 over n squared. Okay, so this lemma here is like the big thing here. This is the important thing. Kind of the point is that like at least half the blocks we like guessing is the best that we're going to be able to do with high probability. So that's what that like indistinguishable is trying to tell us. And so using that lemma and a result about edit distance, we're able to put it all together. So so we're going to let this x hat be the output of our algorithm, where the algorithm is basically it's just going to be is going to be guessing on the blocks that it's unsure of. And then we can say the following here. Wait, what's happening here? Okay. So using facts about the edit distance, we can partition our output string x hat such that the edit distance between x hat and the original string v is like just the indicator vector of how many of these blocks are different. Okay, so we're just going to use this fact about edit distance here. By the lemma that we have, we already know that at least b over 2 of the b sub I are indistinguishable with high probability, which is basically implying that the algorithm cannot do better than guessing for these. And so then all we're really going to do is put together our use of the lemma and this edit distance result that we have here. Okay. And what we're able to see is that in expectation, the output of the algorithm and V are going to differ by at least like b over 4. And this b over 4 is coming from like if the b over 2 of them are indistinguishable, then like in expectation, you're only going to guess half of them correct. And so by a Chernoff bound, you're not going to do much better than this with high probability. So in total, this is how we've reached our contradiction, as we were assuming that before that, remember we assumed at the beginning that the edit distance between this was going to be at most epsilon n. And so you could contradict this and see here that actually like your algorithm can't do better than 16 epsilon n if it's given like less than f of c over epsilon traces. Oh, let me also maybe point out that this is from this particular is from the choice of B, like the way that we set the parameters. Okay. So I know that was pretty quick, but I think at a high level, hopefully it was really not too bad what we actually did here. All we did is we said, look, there are some strings which are hard to distinguish in the exact case. If you construct a string where you're just like randomly taking like a substring of those difficult strings in the exact case and pasting them together, then this string is hard to learn approximately, because it would mean that you have to learn a lot of the blocks right, which is hard. So that's all I wanted to say about the lower bound in the approximate setting. And in general, I hope you got out of this talk that the original trace reconstruction problem is really very cool, and there's a lot of work happening on it as well as its variants. I'm happy to answer questions for a bit, but I hope you, I don't know, consider this realm of statistical reconstruction problems. But thanks for your attention.
Okay, so if there are questions for Sami from anyone?
First of all, I have a comment. So I put in the chat, I hope you see it, the link to
Thank
the
you.
new archive paper that is from February that does the but again, I mean, for this to be useful, quite small. So I guess the other question I had is in terms of what do you know or believe about upper bounds for approximate? Because as you know, if epsilon is a small constant, it's smaller than q, I don't know any upper bound that's better than exact for the approximate problem, though.
No, I'm totally with you. Yeah, so we thought about this for we tried for a while, like about a year, and just really couldn't get anything. So like if you look in our paper, we have this lower bound result, and we have some upper bounds, but the upper bounds are all like of the type of like if X comes from this class, then here's a reconstruction algorithm. If X, which like, you know, I don't want to say it's disappointing, but it's disappointing when like you want, I don't know, in my mind,
What
it's like
kind of what kind of classes are you thinking of here?
So a lot of like the classes that we're looking at are like, they look like very like non-random in that they have some like long runs or there's some long structure that is preserved in the traces, and then you can align with that structure.
Mhm.
Does that make sense? So it's like you have your original
Yeah.
string, there's some pieces which are, yeah, like preserved well enough that you can align by those pieces. For the most part, that's what's happening. There are at least like one of the reconstruction algorithms is actually like quite difficult. And even like it like doesn't look impressive to look at the class of strings, but the reconstruction algorithm itself is like kind of interesting. So I'm sorry. So yeah, so Yuval, to answer your question, I'm not even convinced that that this problem is that much easier, as you say. Like for a small constant, I'm not convinced it's easier than exact.
On the other hand, if epsilon is a small constant, do we know any lower bound that depends on n?
No. So like, yeah, we give nothing for, yeah. So this problem is still extremely open. And yeah, I'm talking about it because I'm not going to work on it anymore. I want someone else to, because I want to read about it. And you know,
So-
like Nina and Russ, like, and you've all been really successful in this problem. So like, let's just get more probabilists on it. Like you all do it.
So do you have some thoughts what happens for smaller epsilon? So as epsilon goes to 0, you get the exact reconstruction problem. So
Mm-hmm.
when it's 1 over n, say. So what happens between log n over n and that? Do you have some?
Oh, right. Yeah, because yeah, ours was only, yeah. Why does our lower bound fail again for less than log n over n? Oh.
Well,
Okay, so my guess would be that it should like at least for the lower bound that it should interpolate. Like you should be able to get a lower bound that just interpolates, right? Like the log n over n was like kind of like a stupid technical thing that like it didn't work for epsilon smaller than log n over n. I would think intuitively you should be able to do something different in that case.
Yes.
I guess it's because your number of blocks is too small. Your number of blocks is too small to get concentration for us when you're looking at epsilon less than log n over n. That's why. Intuitively, I think it should be just as hard.
So I had a question about, so Yuval gave this reference to when the edit distance is bounded above, that this can be done with a few traces, relatively few. And I get why a lower bound on the Hamming distance doesn't really help, but a lower bound on the edit distance, shouldn't that also make it easy to distinguish between?
That's the paper Yuval.
No, that was an upper
in
bound
the link.
on the upper bound on the edit distance, right?
Yeah.
If the
So
two strings are close in edits, then you can distinguish them quickly.
Yes, but if they're very far in edit distance, shouldn't that also be helpfully distinguished?
That's open. And yeah,
So,
I don't know. Certainly we know that mean based is not going to help. So we have, you know, the e to the cube root of n lower bound for mean based reconstruction also applies if you look at pairs that are far in edit distance. So.
yeah, so in a sense you know that there are many pairs that are hard to distinguish.
Yes.
For this
And
many centers.
this n to the 1/3, exponential n to the 1/3, that's the best you can do if you look at one specific bit, or even if you look at all bits, but just the information of
Yeah, just linear information, anything linear.
anything like that.
Okay, maybe
Maybe I stop the recording here and we continue the discussion offline.